Okay, we'll make a start. Hello, everybody. Good morning, good evening, or good afternoon, depending on where you are. Today, I'm delighted to introduce you to this special session on the use of physiological sensor data in travel behavior research. My interest for this kind of started when I started my current project with Charisma Chaudhary at the University of Leeds, where we're looking at a number of different things, but one of the things we're really interested in is trying to better understand the decision-making process and using physiological sensor data to do that. So we wrote a review paper, which is in Transport Reviews, where we basically looked at a number of different applications and we sort of summarized kind of where the field is with this. And in the course of doing this, we came across some really outstanding research, but also identified a number of key areas for development. So the idea of this session is when we heard there was this opportunity to host a special session at BTR, we thought this is a great opportunity to have some of the leading people in this area of research come and talk about the various different things they're doing. So we've got 5 different speakers. We'll have 15-minute presentations and sort of 8 to 10 minutes for questions and answers after each presentation. And you'll notice the topics are very, very different, but they're all on this theme of physiological sensor data. So without further ado, I'll happily introduce the first speaker, my colleague from the University of Leeds, Dr. Vishnu Radhakrishnan.
Hi, Thomas. Thank you. Yeah, my name's Dr. Vishnu Radhakrishnan. I'm a postdoctoral research fellow at Institute of Transport Studies, University of Leeds. I work with the Human Factors and Safety Group. My main research area is using psychophysiological measures to understand and predict driver state and their performance decrement, especially around highly automated driving. In this presentation, I'm just going to present a research that one of the studies that I did during my PhD, which is on using physiological signals to measure driver workload during car following situations and takeovers in highly automated driving. So this project was conducted in partnership with the EU-funded L3 pilot project and with funding from Horizon 2020, University of Leeds and the University of Leeds Driving Simulator, Toyota Motor Corporation, and Seeing Machines, which is an ICE tracking company based in Australia. And also they were co-funders of my PhD program. So a brief introduction. I would actually introduce you to what we call the out of the loop concept, or OOTL, which is the performance problem, which you normally have in SAE level 2, level 3, level 4 automation levels. So what that is when, say, for example, the steering, acceleration, deceleration, so lateral and longitudinal control of the vehicle is controlled by the automated system. Monitoring of the driving environment is also usually controlled by the automated system. And your role as a user would be to be a fallback user. So basically, if the system fails, you need to be ready to resume control. But then what happens is that you don't have enough situational awareness to resume control immediately, and this is something that is known as like out of the loop problem, where you're not really in the driving control loop. What it leads to is poor performance once you have to resume control of the vehicle, which can also impact safety of the vehicle. Sorry, one second. So the driver's workload affects both performance and safety of an automated vehicle, especially when the driver has to resume control of the vehicle from automation. Here, I'll briefly introduce the relationship between performance and driver workload. Usually follows a bell-shaped curve. What you can see is that the center region, this bit is where you have the ideal amount of workload for best performance. The region to the left and right of that is where the performance actually dips. So usually those regions are known as underload and overload regions. And the best performance region is the optimal workload region. Factors that affect performance in underload conditions, I can give you examples, would be monotony and fatigue. Whereas on the other end of the region, high workload induced due to stress, anxiety, an extremely complicated driving situation, or engaging in a non-driving related task, such as using your mobile phone, can all increase driver workload and result in a performance decrement. High and low workload equals poor performance, basically. And in this particular study, we mainly focus on car following situations, because car following situations are a precursor to rear-end collisions, which accounts to over 31% of all crashes in the US. And such car following situations can affect driver workload both during automation and takeovers. We know that previous research has indicated that physiological indices from ECG, which is electrocardiogram, EDA or electrodermal activity, or skin conductance, as some people call it, as well as eye tracking systems, can be used as objective indicators of driver workload. But there's a catch. A host of psychological causal factors can result in similar physiological changes. For example, your skin conductance response can go up due to mind wandering, arousal, stress, workload, anxiety, or even hazard perception. So some of them are good, some of them are bad. How do we identify what is from what stimuli? For that, we need sensor fusion. That is integration of multiple sensors that can pinpoint. For example, if a person is looking at a phone and has high physiological values, if we look at eye tracker where the gaze is, and we know that they're not looking on the road, they're looking somewhere else, and that's causing an increase in their physiological values, that is how we can determine whether it's good or bad. So we need to have sensor fusion of combining it with other metrics such as eye tracking to help identify the causal factors, eliciting the physiological changes. As I mentioned before, ECG, EDA, and pupillometry-based metrics have been used in the past as objective indicators of driver workload. In general, an increase in workload results in pupil dilation, an increase in skin conductance, which is one of the metrics I used in this particular study was number of skin conductance responses per minute, which only takes into account the phasic or fast-moving changes in a skin conductance signal, as well as an increase in ECG-derived metrics such as heart rate and beating rate. We can also derive breathing rate from ECG. Pupil diameter changes due to cognitive activities within 5 to 11% of baseline values. That is, the changes in pupil diameter due to cognitive activity is quite small, whereas changes, it can also be affected by factors such as light intensity, brightness, and those changes are massive comparatively. So this is a brief representation of how it looks. So for number of skin conductance responses per minute, as the workload increases, the number of responses generally would increase. Similarly, for ECG-derived respiration rate, or EDR, your mean heart rate also increases as workload increases, and your pupil diameter values also increase with an increase in workload. But one thing to note is that ECG-derived metrics generally require a higher window for accurate analysis. So if you have short-term variations in workload, such as a takeover scenario, which maybe lasts for about 10 seconds, you can't really look at ECG-based metrics because they need at least 2-minute windows for accurate analysis. And you also need to model the recovery pattern of the signal. That is, usually, I can give you an example that most of you can relate to. If you go for a run, you come back, your heart rate doesn't drop back to normal values until at least 40 minutes later on. So there is that recovery pattern, which you need to model into your signal to understand what is causing the changes, if it is from a previous stimuli or the current stimuli, to make meaningful observations from it. So for the research questions for this particular study is whether drivers' workload during the takeover was varying between the different takeover windows. So how their workload would look before takeover, pre-takeover, takeover, and post-takeover. Whether it was affected by time headway maintained by the automation controller. I'll explain to you what time headway is. It's basically, in car following situations, it lets you know how much distance you're keeping from a lead vehicle, and it's expressed in seconds. So we had two time headways that we manipulated, one short and one long. Short was 0.5 seconds and long was 1.5 seconds. Whether the presence of a lead vehicle during the takeover, that is, if a lead vehicle was present or not when the takeover happened, affected their driver workload. And last, whether the presence of a non-driving related task during automation. So prior to when they were actually required to take over control, they were either monitoring the drive, which is level 2 or L2 as mentioned here, or they were doing a visual non-driving related task wherein they had to find an upward facing arrow from a grid, 4x4 grid of arrows. And that was the level 3 condition. And that was a between participant design. And the metrics we used for analysis around takeovers were pupil diameter, the skin conductance response, number of skin conductance response per minute, as well as self-reported workload ratings. We didn't use the heart rate metrics for takeover situations because, as I mentioned before, you need at least 2-minute time window for accurate analysis of heart rate metrics. A bit about the study design. The study incorporated a mixed design within participant factors of time headway. So we had the short and long time headway, short being 0.5 seconds and long being 1.5 seconds. It means that at the current velocity, your vehicle would take at least 0.5 seconds if it's in the short condition to the front of your vehicle to like reach the rear of the lead vehicle. Similarly, for long condition, it would take 1.5 seconds. So in the long condition, you were keeping a bit more distance from the lead vehicle as opposed to the short condition. The drive mode. So we had drivers doing automated car following where the automated controller was doing the car following situation, as well as they had to resume control and do a manual car following. And then there was also whether or not there was a lead vehicle present during the takeover. So the condition being lead vehicle being present and not being present. And a between participant factor was the level of automation, which basically in L2, they were monitoring the drive, and in L3, they were engaging in a visual non-driving related task, the arrows task. So the takeovers happened either in presence of a lead vehicle, the lead condition, and if it happened in presence of a lead vehicle, it would be either in a short time headway condition or a long time headway condition, or without a lead vehicle. Sorry, it shouldn't be written long there. That was a typo. That's like there's no headway condition there. So this is the experimental design of the study. Basically, they had 2 segments of manual driving, 2 segments of automated driving, followed by 2 segments of manual driving. The red arrow, that the red steering wheel icon that you see is where the takeovers happen. And you can see the blue and yellow triangle, which kind of let us know whether there was a lead vehicle present or not present. All of this was counterbalanced. So in one condition, they would have the lead vehicle present. In the other condition, when there is no lead vehicle, there would be an intersection where the lead vehicle would take an exit, and then the takeover happened after this happened. So these were the conditions that we had, and I'll go on to the methods. So the study was conducted at University of Leeds Driving Simulator, which is an 8 degree of freedom, full motion based driving simulator based on a rail gantry and a hexaprop platform. Has a Jaguar S-type cabin inside it. We had 13 participants in L3 group, 4 females and 9 males with mean driving experience of a mean age of 42 years, a mean driving experience of 22 years. And in the L3 group, again, we had 13 participants, 3 females and 11 males, mean age of 33 years, a mean driving experience of 14 years. I've also magnified the takeover situation, the red steering wheel icon that I showed you before. So basically, there was the automated car following, and you heard a takeover request, which indicated to the driver that they need to resume control. And they had about 10 seconds. It was, they heard, please take over now, with a gradually increasing beep. And they had about 10 seconds to take over control from that point. We considered 3 different time windows around takeovers. So the pre-takeover time window is from when the takeover request was given to 10 seconds prior to the takeover request. The takeover window was from when the takeover request was heard to when they actually resume manual control of the vehicle by disengaging the automation. So they had up to 10 seconds, but they could disengage it at any point by moving the steering wheel or pressing the brake pedals. And the post-takeover window was from when they actually took manual control of the vehicle to 10 seconds after they took manual control of the vehicle. We took 10 seconds as the time window because prior research had shown that your peak performance decrement in driving usually occurs within those first 10-15 seconds, which is why we considered that. And then that is followed by about 4 minutes of manual driving. So prior to the takeover, they had about 4 minutes of automated car following, automated driving, and 4 minutes of, and after the takeover, they had about 4 minutes of manual car following, manual driving. So quickly going through the results, what we saw was that for the first case, drivers' pupil diameter values increased significantly around takeovers, increasing from pre-takeover window to takeover window and to post-takeover window. So there was what I would say a steep increase from pre-takeover to post-takeover. This was observed for both short and long headway conditions. For the short headway condition, there was a significant increase between takeover and post-takeover windows, in addition to significant increases between pre-takeover and takeover window, as well as pre-takeover and post-takeover window. So these 2 windows. And this shows the fluctuation in pupil diameter. It's shown this, the bands, the light colored bands show the confidence intervals, bands, and the dark colored blue and red are like the means. And as you can see, as the takeover request is given, there's a sharp increase in the pupil diameter value, which pretty much peaking around 10 to 15 seconds after they take over. Now, the effect of time headway, drivers reported significantly higher workload levels when they had to resume control in presence of a lead vehicle maintaining short headway condition as opposed to long headway conditions. This was observed for both their NSCR per minute, or number of skin conductance responses per minute, as well as their subjective workload ratings. And it was nearing significance for pupil diameter values as well. But again, the same trend was observed, where short headway had higher physiological values than long headway. Again, drivers also reported significantly higher workload levels when the takeover happened in presence of a lead vehicle, which was maintaining short headway condition, compared to when there was no lead vehicle. This was also reflected in their pupil diameter values. Their skin conduction responses values were again nearing significance, with drivers having higher significance value when the takeover happened in presence of a lead vehicle compared to no lead vehicle. So again, all 3 metrics, we observed the same trend, where when there was a lead vehicle, they had higher physiological activation as well as subjective workload ratings compared to when there was no lead vehicle during the takeover. Quickly, to summarize the results, what we observed was that pupil diameter and skin conductance responses were both able to objectively measure the changes in drivers' cognitive load around takeovers. Their subjective ratings of workload matched with the physiological indicators. Their driver workload increased around takeovers as reflected in their pupil diameter values from the pre-takeover window to takeover window and subsequently to the post-takeover window. So it peaked slightly after the post-takeover window and then started coming back to a normal. The peak in pupil diameter value was observed at around 15 seconds after takeover, also in line with previous literature that indicate performance decrement occur around 15 seconds after takeover. Merritt et al. From 2014 actually found this in their paper. Shorter headways and presence of lead vehicle increased driver workload around takeovers. But this also warrants further research in understanding what are the safe and acceptable time headway margins that can be maintained by an automated controller so as to not result in overload condition during the takeover for the driver. So the driver has to still be able to maintain an optimal workload level without overloading them. And we need to understand what is the ideal time headway margins to be kept from, or the gap to be kept from a lead vehicle by an automated vehicle controller that is acceptable for the driver. So thank you so much for your time. I've put my email and some of my links in case you want to get in touch with me. And I've also provided the links of this work has been published in TRF. So if you want to have a look at that, as well as my thesis, which you can find online on White Rose if you're in the UK. Thank you very much. If you have any questions, I'd be happy to take them now.
Thank you very much, Vishnu. I have a question, but I'll just wait to see if there's audience questions. If anyone wants to raise their hands, if you've got questions. I'm not seeing any hands currently, so I'm going to start with my question. Yeah, so I was in the car for 4 hours yesterday as I drove up to visit my family in central Scotland from Leeds. And to me, I was thinking about these presentations today. I was thinking, you know, how does this apply to kind of what I'm doing just now? I was thinking that for me, the biggest distraction when driving is conversation. Particularly if you've got young children in the back talking to you. So I wondered if there's if you've thought about transferring this sort of work to like driving in the wild, basically in sort of real world scenarios, and whether it's how similar it is, and whether you can capture the more complex workloads scenarios potentially.
It's a very interesting question, Thomas. And I don't know if I've mentioned it to you. The work that I'm currently doing investigates different task modalities. So you have audio, visual, visual tasks. And what you look at is how their workload affects their performance and how it's reflected in their physiological metrics. So what you're speaking about is cognitive distraction, purely cognitive in nature. And one of the things we observe during cognitive distraction, for example, if you're speaking on your hands-free while driving, is your gaze starts concentrating around the road center area, which is where you get maximum information from. So your peripheral vision is kind of not as sharp, where you are more likely to miss out hazards that happens in your peripheral vision. And you would put all your attention on the road center area. So that is an indicator of cognitive distraction, like you said. And, you know, people have used that to differentiate that. Again, the key is to use a bunch of different metrics rather than relying just on one, because, for example, like each metric would have its limitation. If you're using just eye tracker alone, you can look down, you can look at your lap, and you might be either nodding off or sleeping, or you could be looking at your phone, both of which require very different mitigation strategies. So how do you differentiate that? Because your eyes are occluded from the camera sensor. How do you differentiate that? That is where you can use, say, smartwatches or data from your heart rate or skin conductance level to know, okay, he's sleeping off, or he's having a high workload by doing a different task. So combining all three, you can always triangulate the causal factor and provide appropriate mitigation strategy to the driver. Or so some of the things that our lab is currently working on is how you can get the driver back into the loop. So if they're distracted, you can have augmented reality-based approaches that try to get their attention to critical areas that are required during takeovers. So, for example, if they need to perform an overtaking maneuver, you can have, you know, an augmented reality-based arrow that points exactly where they need to do that, or just stuff like that. Or if they need to look at the mirrors, you can try and draw their attention to their rearview mirror. So, based on the causal factor, you can provide appropriate mitigation strategies that can help the driver. And this is particularly of crucial importance because there, as of 2025, I think, it would be a legal mandate that all new cars on the road in the US as well as in Europe would require to have a driver monitoring system.
Wow. Okay. Great. That's really interesting. Thank you. Thank you for that.
Thank you. Thank you.
No problem. Any further questions? Yeah, no, not seeing any. So yes, there's your emails there for if anyone else has questions at a later point. But yeah, we'll now move on. Thank you. So next up is Rana Tarabay. Are you able to share your screen, please? Yes, perfect.
Hello, everyone. My name is Rana Tarabay. I'm a PhD candidate in the Civil Engineering Department at The Ohio State University. My research interests include emerging technologies in transportation and behavioral modeling with discrete choice analysis. It's my pleasure to present my research work with Professor Maya Abu Zaid at the American University of Beirut. Our paper is entitled A Dynamic Hybrid Choice Model to Quantify Stress in a Simulated Driving Environment. I will start first by motivating the study. Road traffic crashes remain a leading cause of death. According to the World Health Organization, road traffic crashes are the first cause of death among people aged between 5 and 29 years old. And each year, there are 1.3 approximately million people killed on roadways. In Lebanon, road traffic crashes are the 7th cause of death in 2020, accounting for more than 3% of the total deaths, also according to the World Health Organization. Driving error is a major cause of crashes, and based on data collected in 2010, it is estimated that 78% of crashes in Lebanon involve driving error. In this slide, I show a model of driver stress that was developed by Matthews in 2002, based on Lazarus' work. In this model, the cognitive stress processes are affected by personality traits such as the dislike of driving or aggressiveness, and environmental stress factors such as bad weather, traffic jams, and high workload. As a consequence of these processes, or the stress may lead to some subjective stress symptoms like tiredness, anger, and worry, in addition to changes in the performance, such as loss of attention, impairment of control, and risk-taking. Our study aims to answer two main questions. First, how does the secondary task and its level of difficulty affect driving performance and physiological measures? And to what extent may there be self-regulation in driving to allow the performance of the secondary task? Second, how does stress arising from workload carry over from one time period to another while driving? I go next over the methodology. So to answer basically our research questions, we use a driving simulation experiment that involves a primary task of driving and a secondary task. For the secondary task, we used an auditory vocal task with varying levels of difficulty while driving through a set of critical traffic events, which I'll explain in the following slides. Throughout the experiment, we collect measures of driving performance and physiological indicators, and we model the driving behavior and the stress evolution. We use a sample of 74 AUB students with age range between 18 and 28. As for the apparatus, we use the driving simulator at the American University of Beirut from Drive Safety, and we also collect information. We collect physiological measures using a MEDAC system 3 sensors. We use the EKG sensor to collect the heart rate measures, and we use the skin conductance sensors to collect the sweat activity or the skin conductance while driving. As for the primary task of driving, we design 3 road events derived from the urban context and considered as type of surpass type events. The first event is a pedestrian event. So pedestrians would cross suddenly in front of the driver. The second event is a truck that suddenly stops in front of the driver. And the third event is an intersection with a traffic light that turns red suddenly. As for the secondary task, we use the NBAC task that has 3 levels of cognitive load, which is designed by the MIT Age Lab. And this task is designed to simulate the type of cognitive load that comes from conversing with passengers in the car. So this task has 3 levels of difficulty, and it is based on some audio instructions that the driver will hear while driving. At the lowest level of workload, the driver will be asked to repeat a set of numbers, and at each number, the driver is asked to repeat the number that is just said. Whereas at the 1 back level of this task, the driver will be asked to repeat the number that is said 1 number before the number that is just said, which involves basically maintaining 1 number in the memory while driving. While at the 2 back level, the driver is asked to repeat the number that is said 2 numbers before the number that is just said, which requires holding 2 numbers in the memory while driving. So we can see how the increase in the cognitive workload comes from the 0 back to the 2 back level of this task. Our experimental design, basically, in our experiment, we had 2 types of scenario variables: the driving events, which are, as I mentioned previously, 3 road events: the truck, the pedestrians, and the traffic lights, which are randomized across the experiments across the subjects. And the secondary task level variables, which are the levels of the secondary task, which are also randomized across subject in the experiment. The experiment involves 2 phases: a control phase in which the driver is only subjected to the road events without being subjected to any additional workload, and the treatment phase in which the driver will be subjected to the secondary levels of the levels of the secondary task, while also encountering the 3 road events. And this is designed in such a way that at each road event, the driver will be subjected to a specific level of the secondary back task. In addition to a baseline test, so we have basically a baseline, a control phase, and the treatment phase. The order of presentation of control and the treatment was randomized across the subject as well in the experiment. As for the modeling approach, we define 7 time periods that characterize or represent the drive, with T0 being the baseline time period. And in this case, I'm showing a control phase coming before the treatment phase. So T1, T2, and T3 are time periods that correspond to the control phase in which the driver will encounter the 3 road events. And then T4 to T6, we have 3 time periods that represent a treatment phase in which the driver will be subjected to the secondary back level task together with the road events. We model in this study the state stress as a latent variable. So basically, this is a variable that is not observed. However, we can measure it indirectly through the measures of driving performance that we ended up collecting from the driving simulator and the physiological measures that we collect from the physiological measures. So basically, these measures were used as indicators of the state stress. And we we measure the evolution of these indicators and measure throughout these 7 periods in the drive. In this slide, I show the modeling framework. So we use a dynamic hybrid choice model with a serial correlation. In this model, we represent, or we include an agent effect, which is basically a random term that represents a trait, a personality trait, or an individual characteristic. And this random term basically influences the state stress at each time period. And it's common across all time periods. So we can see here time t -1 followed by time t. The blue part in this model represents the latent variable model, while the orange part represents the choice model. The state stress is affected by the scenario variables at each time period. For example, at t -1, the scenario variables, as I mentioned previously, include the workload levels in addition to the road events. And we use the driving performance and the physiological measures to quantify the state stress, or to measure the state stress. So we can see a measurement equation between these two variables. As for the choice model, the choice basically is an indicator of the utility. So we see here a measurement equation, whereas we see a structural equation coming from or between the latent variable state stress and the utility function. And same for the time period t. And again, we model dynamic using the serial correlation in this model. I'll start first by showing the equations briefly for the latent variable model. So we have the state stress latent variable that includes a constant in addition to the scenario variables, and the agent effect, which represents the individual or personality trait, as I mentioned previously, and a random disturbance term. In this specification, we include the pedestrian variable as a binary or as a dummy variable, and the traffic light event as a binary variable. So basically, our results would be compared to the truck event, which is considered in this case as the reference. Whereas for the secondary task scenario variables, those are the 0 level, the 1 level, and the 2 level. And those are also included as indicator variables, and they are compared to the control phase, which is here included as reference. Moving to the measurement equations, in our study, we use as I mentioned previously, driving performance measures and physiological measures. And those were based on the statistical analysis that we made at the initial stages of our study. And also based on several evidence that we found from the literature. In terms of driving performance, we use the maximum speed, the maximum accelerator pedal depression, and the reaction time as indicators of the state stress. And we also use the maximum heart rate as an indicator of the state stress as a physiological measure. In this equation, we have a constant, we have the factor loadings, which represents the effect of the state stress on each of these indicators or measures, and we have a measurement error term included in the equation as well. Moving to the choice model, I show here three equations, basically characterizing the decision whether to cross or not the red light at the intersection event or road situation. So in the first two equations represent the alternative or the decision to violate, and they include the state stress latent variable. We have the coefficient, the beta here, that quantifies the impact of that variable on the utility of violating the red light. We use two different constants in these equations, since the first three could be either the control or the treatment. So to account for that, we allow this variation among the estimated coefficient for the constants. As for the don't violate alternative, it's basically 0, so we don't include any variables, and we include the random disturbance term. Similarly, in these two equations for the violate alternative. We estimate our model via a simulated maximum likelihood, and we use Python Biogen for that. Next, I'll go over our results. So this slide shows the model estimation. We noticed that the majority of the majority of the estimated coefficients were significant. Specifically, the scenario variables were significant, and also the factor loadings in the measurement equations of the latent variable were also significant, reflecting or implying that these are good measures of the state stress. To summarize, in general, our finding, the secondary task and the load events were found to increase the level of stress in our experiment. Individual traits were found to affect the level of stress as well. The stress causes some self-regulatory behavior and increase in heart rate, but the effect on the road safety may not be very substantial for this experiment in our case. However, repeated self-regulatory behavior may cause depletion of resources and endangers driving safety. To conclude, the driver's state stress is found in our study to be significantly affected by the road events or situations such as encountering pedestrians, trucks, and traffic light. The level of cognitive workload, which was in our case coming from the secondary task, and the individual propensity for stress, which is in our case was the agent effect, and the mere driving task, which is basically could be to maintain the control of the car while driving. We also found that there is a pattern of regulatory driving behavior in response to the increasing stress. Our model is basically a mathematical conceptualization of the transactional model of the driver stress, and it can be integrated within in-vehicle systems to detect and predict the driver's state and enhance safety and well-being. Finally, I'm listing here our publications in IEEE transactions on intelligent transportation systems and in transportation research part F, if you would like to learn more about our research at the American University of Beirut. We also would like to acknowledge the University Research Board and the Dean's Office for supporting this research at AUB, the research assistants who help at different stages of this project, and all the students who volunteered to participate in the driving simulation experiment. Thank you so much for your attention, and I'm happy to take any questions.
Great, thank you very much. That's really interesting. I have questions, but I'm going to see if there's anyone else again. I don't want to be first every time. I'm not seeing any hands yet. Okay, I'm gonna go into my question. So I'm really interested in your model formulation there. One thing we've found with choice models using data from driving simulator is that, because of course you're limited by sample size, you can't put too much into the model. And I was wondering in particular whether you tried that in terms of, did you try putting in social demographics into your latent variable, for example? And in particular, I wondered about driving experience, because I think you had quite a young pool of participants. So I wondered whether driving experience, you looked at that, whether that would have an influence on your results.
Yes, we actually tried these variables, the demographics. We tried several variables such as the gender, the age, and we also included the driving experience and the structural equation of the state stress. However, the estimated coefficients were not found to be statistically significant at that time, so we ended up removing them from the structural equation of the state stress. But yeah, as you mentioned, those are, of course, very important variables to test or to try in order to better understand the driving behavior in general.
Yeah, great, thank you. Couple of messages in the chat. So questions, how did you assess personality and which questionnaire?
Yes, so regarding the personality, I should mention that there's one or in the way this experiment or driving simulation experiment was administered, it's basically we had a driving simulation experiment followed by a subjective questionnaire. So basically, after each participant drives the driving simulation experiment, they were given a set of questions, a set of statements that assess their personality traits, and those included statements, for example, related to driving enjoyment or aggressiveness or a set of related trait characteristics. We tried to include these statements or the responses on these statements as indicators of the agent effect. So we tried to include these as measures or indicators of the latent variable. That was not observed. However, the factor analysis did not give us a good representation of these statements in terms of the traits. So we ended up using the agent effect as a general trait or as a general personality trait without having without measuring it through particular statements from the survey, I mean.
Thank you. Any final questions before we move on? Okay, not seeing any, but yes, that was no, it's really great. Thank you. And
thank you so much.
Yeah, no problem. Great. Thank you. So Prateek, yes, you're next. Perfect to see your screen on.
Thanks so much. Let's get started.
Thank you very much, in particular, given your time zone.
Yes, thanks, Thomas, for inviting for this seminar. I'm Prateek Bansal. I'm an assistant professor at NUS. It's around 3 a.m. in Singapore, but I thought like it's better to be here rather than sending a recorded presentation. So I'll be talking about how do we inform ethical decisions of autonomous vehicles through video-based choice experiments and brain recordings. So let's get to the topic. So basically, we have been talking about the trolley problems for a very long time, but they are becoming realistic now. So the trolley problem is a very traditional ethical dilemma where, let's say, a trolley is going in a specific direction, and if it goes in that direction, then maybe it will kill a lot of people or a family with a dog and children. But this person in the green has a green sweater, has all the rights and power to change the route of the trolley. And if the route is changed, only one person, maybe a single person, will be killed. The question is it right to do or not? And it is no longer a situation which is hypothetical. These are the situations that we are going to face in the near future. So we need to understand how autonomous vehicles need to really make these kind of ethical decisions, because they are very important for their wider acceptance in the future. And it has been established in a I wouldn't say recent, the paper that came in the Nature in 2018, that yes, there are subjective beliefs of the population which play a very critical role in understanding how people want autonomous vehicles to make the decision, right? So there are mainly two aspects. One is how people want autonomous vehicles to make the decision, and third is how policymakers will in the end decide. So we are not looking at the second question. We are first looking how, if autonomous vehicles have to make a socially acceptable choice, how would they go about it? So the point that we are going to make, the model machine experiment was mainly the image-based experiment, but we think that the video-based experiment and brain data can give us some more interesting insights. So if we think about it, why? Because in the model decisions, there is no right or wrong decision. So your internal factors, which may include your human personality, socio-demographic experiences, and subjective beliefs, all these can also affect your choices substantially. Then your external factors and internal factors may have interactions that we are going to see a bit in our results as well. And when I say external factors, they are mainly sensory information that respondent sees in the experiment. And why we think that the brain data can help us in identifying something more than just the response time or maybe the choice data, because there are clear biomarkers for the internal factor processing and the external factor processing in the brain regions. So it is like generally the occipital region, which is the back of the brain, is considered as processing the sensory information, and the frontal region is considered processing or maybe driving the information from the top-down factors, which come from more internal factors. Okay, so top-down is related to the internal factors, and bottom-up process is related to acquiring the sensory information. So considering there is a literature in the neuroscience, but it has not been tested in the model decision-making literature, and not even in the there is some literature on using brain data in economic decisions, but not so much in the moral decision making. So that's also another reason that we are interested in looking into it. So if we look at the research question that come out of this can we learn information acquisition and decision mechanisms in moral decisions using brain data? And can brain data help identifying appropriate approach to collect social attitudes in moral decisions? These are the two main questions that I'm going to talk about today. We are still working on how do we incorporate this brain data into behavioral models and really get more insights about these biases. So we have some framework already in mind, but I will not talk about that in interest of time, but we'll give you the flavor of what we already have in related to the first two questions. So what we do is to simulate a situation, simulate a trolley problem. We simulate a situation where an autonomous vehicle comes on a roadway, and autonomous vehicle has no choice but to hit one of the two pedestrians approaching from the both ends of the road. And we do this experiment in the video and picture-based scenarios, and I'll show you the video just to clarify what I really mean by no option to save both pedestrians. In terms of external factors, what we do is we vary the age and gender of the pedestrians. Internal factors, we also ask a lot of attitudinal questions, but in this presentation, I'll focus mainly on the internal beliefs which are governed by maybe encompassed by the age and gender of the decision maker. So we will see some heterogeneity and how the brain movements are different in those situations. So what I'm going to do in terms of, after talking about the experiment design a bit, I'm going to compare the choices and brain activity in video-based and the picture-based experiments. Then we will see if the brain activity reflects the impact of external factors. And then we will try to explore some internal factors. And in the end, we will conclude by identifying a biomarker which really connects the information processing and the choice biases that we observe. I would just say that these are very initial results. We are doing more rigorous analysis as of now to make findings robust and make sure these results are consistent. Okay, so this is how the experiment looks like, where the participant has EEG on hand and two pedestrians are coming on the both sides. And basically, there are two keys that respondent uses to move the trajectory of the autonomous vehicle. And there is a sound as well. And because of the sound, we had really hard time in getting the IRB approval, but we could convince them that, oh, this is what your autonomous vehicles are going to face in the future. So why not we just put respondents in that situation now? Anyway, so let's get to the, this was the video-based scene. In the picture-based scene, what we do is we show them the before situation, before the crash situation. This is on the left panel. And then we give them two situations, option 1 and option 2. In option 1, left pedestrian is killed. In option 2, right pedestrian is killed. And these are just basically screenshots from the video-based experiments. And here we use the 40 participants, sample of 40 participants, and the age is 20 to 40 years. These are students and staffs, and we make sure the balance in the gender. And we make sure for randomization that 20 participants engage in the video-based experiment first and then the text-based experiment. We also make sure this randomization within the males and females. So basically, 10 females see the video-based experiment first and the text-based experiments later, and the same for the remaining. In the stimuli side, we vary the age and gender of the pedestrian in a random fashion. And there are other randomizations that we do. For example, the position of the autonomous vehicle is randomized where it starts, and many other such things we take care to make sure that they do not bias the result. And 16 randomly generated situations in picture and video-based situations are shown, and each is repeated twice. So we show 32 picture-based and 32 video-based experiments, but still we could finish one participant's experiment in around 40 to 45 minutes. The EEG calibration was easy because it is not the wet electrode, it's a dry electrode, which is much easier to fit and forward. So okay, so let's get to the very first result, which you might be interested in seeing. Like, is there any real bias in terms of saving specific demographic groups in the population? So what I'm presenting here, if you look at the left plot, on the x-axis you have male and female, which is the gender of the pedestrian, and on the y-axis you have the probability of saving them. So we can clearly see in the both video-based and the picture-based experiments, females are more likely to be saved compared to males. And if you look at the right plot, where we see that the children are more likely to be saved, and then the young people and the old. Well, the result is obvious, but the extent of this bias is the new finding, I would say. To be precise, the results are aligned with the moral machine experiments in some sense. And thanks to Thomas, because he asked us to really verify the results with this, and that helped us to make sure that the results are consistent. So here, this specific plot actually tells us that maybe we don't get much from the video-based experiment compared to the picture-based experiment. But we will delve deeper into it when we go to the internal factors. When we look at the respondent level heterogeneity, we will see some differences, and I'll try to connect that with the brain data in the next few slides. So now what we do is, it's just a lot of information. So first, I would like to organize what we have here. So we first look at the event-related spectral perturbation, which is just a way of describing the neural activity in the different part of the brain. And we look at the three frequencies, theta, alpha, and beta. On the three panels that you have, left is theta, middle is alpha, and rightmost is beta. In the left one, if you look at the picture-based video, I first show the picture-based topogram. It's the brain image, and video-based scene. And the third one is the difference of the video-based and the picture-based. And we do that for all three frequencies. So what is interesting, we look at the theta. In the theta band, we can clearly see that there is a focus in terms of there is a more movement of the neurons in the occipital area, but this is substantially higher in the picture-based scene. This movement is in the occipital area is much higher. That generally means that the sensory information is acquired voluntarily. And we expect that to happen in the picture-based experiment, because you are not in an environment, you are looking at the picture-based experiment and trying to acquire that information. So that's why you see more neural activity in the occipital area. Similarly, if we look at the alpha and beta, we also see more in the occipital area, but it's more diverse. But if you look at the differences are more in the occipital area. So if you look at the beta, we couldn't find the much interpretation of the alpha, but we could find the interpretation of beta in the literature, which is the rightmost panel. we see that in the video-based experiments, the ERSP in the beta band is relatively lower. The relatively lower beta band ERSP implies the more engagement in the situation or emotional engagement of the respondent, and which is we have established literature on that, so we don't need to reinvent the wheel there. So that means that in video-based experiments, the respondent is relatively more engaged in while they make the decisions. And let's see if when we look at the heterogeneity in the choices, do we see some differences, and can we see some justification based on this data? So now what I show here is on the left panel, I show the bias. So on the left panel, I look at the male and female pedestrians, and on the right panel, I look at when the pedestrian age is varied, child, young, and old. And on the left panel, we have the male and female. So if you look at the first at the right panel, the top figures are for the heterogeneity in the gender of the respondent, and the bottom figure is heterogeneity in the respondent of age. So we can see that in both picture-based and the video-based experiments, there are no substantial differences in terms of the pedestrians' age valuation, or we don't see much differences there, irrespective of the gender of the respondent or the age of the respondent. But what we see on the left plot, if you look at the top panel, in the picture-based scene, the gender of the respondent is not affecting their preferences for the male or female to save. The bias is similar in the female respondents and the male respondents. But you can see in the video-based scene, females have higher bias compared to the male respondents. And this is interesting, and this result has been is there as well in the model machine experiment, but we could identify this result in video-based experiment with very small sample size. But if we would have just done the picture-based experiment, we could not identify this result. So video-based scenes really, with the emotional engagement, they are able to identify those biases much clearly. So we are hypothesizing that maybe with a smaller sample sizes, you can identify these biases with the video-based experiment, even if overall the choices are not very different in the picture-based and the video-based scenarios. The other thing is the other reason why we might not see differences in the video-based and the picture-based experiment in the age choices are much simpler compared to the gender choices. And we see in the cognitive burden, when we look at the topograms in the age, when they need to choose the same gender pedestrians, but different age, it's very easy choice for the participants. But when they need to choose same age, but different gender, and they need to decide whom to save, it's a much more difficult choice. So that difficulty in choice, the information acquisition, we see that more in the gender-based different scenarios, and that's why that is reflected. The differences are reflected in the picture-based and the video-based scenes, especially in case of the gender of the respondent, and as well as gender of the pedestrian. So what we tried to do is we did a very basic regression of the biases with the ERSP in the all three bands and the gender. And what we find is the beta band is significant, which kind of explains that how people are emotionally engaged in that decision. That really helps in explaining that choice bias that we are finding in the video-based scenarios for the male and female respondents. So in summary, people demonstrate gender and age biases in choices. They most probably save female and child. Age bias is more stable, so that the presentation type doesn't affect it. And as I said, it's an easier choice for respondents compared to the gender. And presentation type affects a gender bias, and certainly it becomes different between male and female respondents in video-based experiments. And change in bias is predicted by the brain activity in beta band. That's an initial result that we have, but we need to delve deeper into it. And we have kind of with the theta band differences, we see that the picture-based experiments lead to more voluntary search of information. We validate this with the brain data, and with the having the beta being significant factor, we can say that the video-based scenes emotionally engage people, and therefore bias is more pronounced even in the small group of participants. Thank you. I'm happy to answer any questions you have on this one.
Great, thank you very much. Anyone got any questions? Otherwise, I'm going to ask questions again. Okay, I'm going to start with mine again. This is the third time I've seen sort of a version of this presentation, and each time I think of more things. I think this is really exciting work. So the thing that struck me, one of the things that struck me at the mathematical psychology conference that I was at a couple of weeks ago with your postdoc Vladimir, was the number of people who looked at sort of reinforcement learning type work. And I wondered if there's any scope for that, given you've actually got 32 choices, whether there's actually some amount of learning. And I'm thinking, what kind of learning would there be in this? And I think it might be just that people get more used to the situation and therefore maybe become less emotional. So I always wondered if that bias, but these biases might diminish over the course of the 32 choices, for example. And the other way it might manifest itself would be if people maybe didn't just, so I don't know if you have this data, but in the video-based data, they use the keys to respond left or right. But do you know if they've not responded?
Yes. So in the video-based data, okay, so I'll answer the second one first about the video-based data. So so as of now, there is an option of not responding and really hit the pedestrian without responding. We actually remove those from the respondents in the analysis because it was very difficult to identify whether it is a conscious choice by the respondent or was it just missed by the respondent.
Okay. Interesting.
Yeah.
Okay.
Yeah. And regarding your question about the reinforcement learning, I think there is a value in it, but in terms of if you think about the policy implication of that, it has long-term implications, right? I mean,
no, yeah, it's a good point.
When people keep seeing these things again and again happening, how that will affect their behavior. So I feel people might not be super interested at this moment about that, but maybe down the line, like after 5-7 years, when technology is more mature, then they might be interested in this kind of learning type of experiment. But at this moment, what we are thinking is we are thinking of developing a customized sequential sampling model where we try to understand where there is a drift rate is affected by the response across the respondents, or whether there is a collapsing boundary type of a model where whether the boundary is different across the different situations. So we are thinking in that direction just to kind of justify the biases through the model parameters.
Yeah. Okay, and there's quite a few of the versions of these models that have a sort of non-decision time.
Yes.
And that's the sort of thing I can imagine you could maybe link in if you actually reuse those ones without it. Yeah.
Yes. So we are thinking in customizing a traditional drift diffusion model and see if we can model it and get some connections with the brain data and the response time data that we have.
Yeah, okay, great.
Yeah, thanks.
Yeah, I look forward to hearing about that. Yeah, no problem.
Yes. Maybe in IATBR or ICMC, we will be able to.
Nice. Yeah, okay, looking forward to it. Great.
Thanks, Thomas.
No problem. Any further questions? No. I should say that I believe this video will go online on YouTube, so people should be able to look at this later. So we can advertise it to our colleagues, and Yusak's already said you'll email it to the IATBR mailing list. So yes, we may all find we have more questions later. Thank you very much, Prateek. And yeah, on to Yusak.
But by the way, Thomas, before I start, there's actually 2 questions. Probably from.
Oh, have I missed those? Sorry. There's a separate Q&A. Sorry, I missed those. Sorry, Prateek, are you still there? Yeah. Sorry, there's a separate Q&A section. I hadn't missed that on Zoom. I was looking at the chat. So first one is, couldn't you get an EEG from them while they were using the simulator?
So we don't have a proper driving simulator here. We have our ad hoc arrangement where we designed this experiment in Python-based interface. And it's a video-based experiment where they're not really doing the steering, they're just controlling with the keyboard. But about the second question, EEG exam with several degree of freedom in simulator. EEG can be used, but it is very sensitive to the motion. And there might be a lot of artifacts if you start moving the respondent. So it's not very wise idea to do that. But if we want to do that, the best strategy can be if you incorporate this with the VR environment with EEG and you move the VR. You move the VR environment for the respondent rather than moving the respondent itself and just record the brain data. So we are trying to do this strategy with some new MSc students. We are just trying to find some way to ad hoc way to connect the VR and EEG together. And I feel that is a better way rather than let the respondent move while they have this content.
Thank you, Prateek. And sorry, Ali, for having initially missed your questions there. Perfect, great. Okay, so yeah, Yusak.
Right. Thank you. So I'll share my screen. Okay, so I guess you will see my presentations. Can you see my presentations?
Yes, thank you. Yeah, perfect.
Great. So my presentation would be quite different compared with others. My title is supposed to talk about cognitions and behavior research based on psychological measurements in virtual reality. And I put learning of doing. Because I think if I have to introduce myself first, so I'm a professor at POCO in Vienna. And then the work that I do basically is collaborations with colleagues, Martina Fiedler, who can't be here because she's in maternity leave, and Sunshine Robin, who actually among the audience. So they can also answer questions if you have questions. But our questions or our interest is not only taking data from the sensors and analyze as it is, but we kind of questioning whether all of these things is actually good enough. And then if it's not good enough, how then we can actually utilize it. And if it's good enough, we actually overdoing it. So this is kind of the things that we're actually doing, whether with sensors is good for just one sensor or and one. So that's pretty much what we do. And when I sharing these presentations, I'm actually not familiar with this BT audience of preparing a little bit from the backgrounds, how to set up an experiment. Now I have the previous presentations, probably all audience are experts already, so I'm not quite sure. Let me go through probably just one or two months, probably not quite sure what we're talking about. We're talking about virtual reality and application in transport. So I'll talk a little bit about that and what the common procedures actually doing those. And then given that, like we will case study, then we actually analyze and shows how we did and get a conclusion. And we actually learn by putting all these together. Just if you actually also want to have one for your own university. Just one step back. So although we already have 3 presentations about very advanced stuff, probably it's nice to now we focus on virtuality. So what is virtuality? So it's basically, it's for us, it refers to computer technology that uses software to generate realistic images, sounds, and other situations that represent immersive environments and stimulate user physical presence in this environment. So if you are not familiar with it, I always talk with my students, encourage them to watch this movie. I'm not paid by the studios, but I thought Ready Player One is really nice, where you can actually be somebody in spiritual environments and eat, and whatever you suffer there, they have to also get something back. So why do we actually use, why this kind of technology is actually exciting? Because as you can also see from the previous question, basically this technology can actually allow us to explore sensitivity, or we cannot really test, or just the cost is so much worse. For example, if we want to change the configurations of the traffic, so if we actually do a real experiment, real life, that will cost ton and something else. And then another thing is also kind of help us to do some stated preference. It's much more practical. And so instead of you have this long, boring, different 100 different blocks of combinations of variables, you can also show this in the pictures, like what just Prateek actually did. Then you actually do it multiple times, and people also still get excited. But then at the same time, we can actually do this in a very controlled and basically valid environment, internal validity. So in that sense, actually really great. And this is not actually first. In the last 5 years at least, there have been a lot of implementations of this technology in the different transport and so training circumstances. At least for like previous presenters, we also want to know, actually use these technologies to understand people behavior and choices. What would be the trigger people behavior, and at the end, basically, we can actually understand decision-making processes. So then we can actually, at least for us, the ambition is in PNI is that we want be able to design more livable city. This is how we actually setting up our lab. So we actually have a hardware and software. So basically, we do have of course, the machines that actually generate kind of link and generate the environments as we wish, but then we also have the end sensors. You probably have heard many times and seen a number of times, these EEG, smart band, eye trackings, all sensors that you actually put on your skin, etc. And for us, currently we do have e-scooters and bicycles, so it's multimodals. You actually play this, already be able to play these two modes in one simulations. And what also difference with us is that we can take off those simulators into a real life. So then we can actually do some kind of comparison. So why we actually do this, because for us, we keep questioning whether whatever you actually measure these VR environments, whether it's actually reliable in a real life environment. If not, it doesn't really matter how fancy our model is, garbage in, garbage out. So the software we use for the traffic simulations, we use PSIM, but then we also use other software that you also use, I guess, City Engine, Unity, Steam, Empatica, and so on. So how do we do these VR experiments? The first one, we do these scenario creations and we do kind of testing. Then we also, again, use these mixed data collections, both from sensors and observable and also studied data. So for example, for personality, we actually use questionnaires that has been used by NASA. So then we actually set the scenarios, at least for us, what we do, because we really want to test some things that actually really real. So we actually use Vienna as the environment. So we actually create a VR versions of the city. So we actually start with this basic city plans that we have. Then we actually also combine these 3D modelings. Then for the transport, we use VSIM based on the odometrics that we have. And then voila, then you can actually get a different travel scenarios. Currently, we try a different blob. We start with the ring. We haven't really completed the whole ring, just one segment yet, but we hope that we can actually improve further. If you've been to Vienna, this is pretty much what you see in Museum here. Because again, our emphasis is also try to understand the interactions, not only the data that we get from the sensors then we put in the models. We also want to know how people actually interact with the sensor itself and also with the machine itself. We do two different tracks of research. The first one is more theoretical. So we actually want to know, for example, how good is the sensors actually records our reactions and behavior. And in this sense that has been presented previously in ITBR and WGTR recently in Montreal is basically detections of hazard perceptions. So how valid is this, and how different sensors in our brains with this EEG is actually consistent, and how this is actually predictable. And in doing so, we also try to test two different theories, whether this is just you read and then you react, or there's some kind of memory when you're actually doing so, and this memory will actually continuously enforce your decision, your next decisions. Whenever, for us, this is just when the door open and throw the balls, whether people actually have to avoid and so on. Then on practical side, because at least in Vienna, whatever we do, we also need to actually show to our stakeholders that it's actually useful. Because we actually do e-scooter, so we actually try to understand how people actually interact with e-scooters. But then, like Robin in KTH, they collaborating with Ericsson's and also Scania, we also test this with remote driving. So it's pretty much like this out-of-the-loop system that earlier Vishnu actually mentions. But we also test with the real car, and we drive remote with real car. So for the next, the case study that we're actually going to discuss, we will actually just focus on the one that we actually did in Vienna. We want to know the impacts of the different configurations of the roads to the e-scooter users' stress. And then it's pretty much like these arousals that I think Vishnu or Rana actually mentions that this is kind of reactions when you actually have a different configurations off-road users in your lane. So why e-scooters? At least in Vienna, it's actually super important because currently e-scooter actually has been started to be banned in the different European cities. But then Vienna actually take a different path. We actually built more than 200 mobility hubs, which have shared modes, including e-scooters. So we have tons of them. Now people actually start confused whether they should actually go with bike routes or should drive with roads or pedestrians, or just like other cities, throw them away. So this is why we actually bring VR in, because then with VR, then we actually know with the different road configurations, then we know how actually people actually react, which we cannot actually do with just real life observations. So in particular, the studies that ongoing studies that I'm going to briefly present the output is just to explore the applicability of what we call social force models to explain psychological stress for the e-scooter users. So the social force model is pretty much like your reactions or behavior on the road space. It depends on the characteristic of your movement, and also your groups, and also your directions, and also other people movement and group and size on that same given space, and including the distance between you and those obstacles or those continuous movement on a given road space. So given this, then if when we actually test this in VR, so then we can actually know in which circumstances then would best we can actually put e-scooters in a different road setting. So the experiments that we have, and this is segment of the road in Vienna, is we actually test different scenarios where basically people will confront it with bicycles, people crossings, also traffic light, and whether they will be along the same directions or across same directions. And our hypothesis, just a very simple one, basically the faster then the rider can actually reach the desired speeds with probably lower stress. It's because it's also indicate that the driver may also have much less obstacles during the journey experience. But then at the same time, the same amount of increased traffic, the smaller or the more basically obstacles in your routes, and the bigger they are, then you probably just increase your stress level. So what we did is pretty much last year, we actually have 10 different tasks for our participants. We actually have 36 participants. So when we recruit this, we recruit among our students and staff that is actually not working or within our immediately with the research, but somebody else. And then to reduce the participant workloads, we actually also our respondents and also the researchers, we actually also have these two-way data collections. So then it's actually, although we only have 36 participants, as other studies probably shows, we actually also deal with a huge amount of data sets. Data sets that we do have basically a perceptions data. And this is, again, this is something that we actually ask, and then we also use this NASA scale. And then we also have the socio-demographic data that we actually ask them, screening earlier questions to make sure that everything is comparables. And from the sensors, we do actually have behavioral data from the vehicles, where the accelerations, velocity, turning, tilting, brakes, etc. And then from the sensors, we do have heart rate and skin activity. That's pretty much same as what Rana actually put on the skins to also to measure the level of stress and also the EEG. And this is pretty much the descriptive statistics that we have. So we do have a higher proportions of male and young and certain nationalities, but then they also better educate, and some of them are actually quite familiar with e-scooters. And then this is just to show the distributions of different variables, including the heart rate itself. So then when we actually do this, we do a multivariate analysis. We just find the heart rate relationships with also the time-related stress variables and distance-related variables, and also from socio-demographic data. And then what we found is scooter accelerations is basically, well, basic fasters, or the sooner you actually reach, and your ability to actually maintain your speeds at your desired speeds is also positively correlated with your lower heart rates, which kind of confirms our hypothesis that it also shows less distractions along the corridor. And then when you actually see this kind of social force models, basically kind of the impact of the size, again, in the sense, in these models, we actually keep the size same, but the impact of the size and the distance to the person. So given the same size of the obstacles, basically, the closer it is, then the more it's actually give you a higher level of stress. But then at the same time, the more you actually ride it, so the more you're actually familiar, you are actually in active e-scooters, stress actually experience. And then the one who actually got the highest heart rate is people among 30s. And then after that, followed by the younger people between 25 and 30. And then the younger, higher than 35 is the one that have the least heart rate. So what have we actually learned from these experiments? First one, so this is a very general, if you want to setting up these things. So first one is setting up a VR environment is not just straightforward, it's actually take a different thing, especially if you want to replicate a reality, in particular, combining 3D data. And then synchronizing multiple sensors sometimes is also takes some of the work. And if you actually notice our pictures, they actually don't really use Google anymore, because the more you actually involve tilting and so on, then the higher probability you actually have this motion sickness. And as Thomas mentioned earlier, when you actually start doing this, you actually have a small sample size. That's also a limit in our capability to actually deploy much complex discrete choice analysis, especially when we actually also want to actually introduce this kind of panel construct. But then nevertheless, the system actually able to actually collect the data that we could or would like to collect. And then what also interesting when we're actually doing this is we able to well, at least we have to go through an experiment on how should we actually set the data sets, because it's quite new for us, but probably not for others. So this is also takes some time, but nevertheless, it's this kind of data actually able to reveal some kind of relationship, which also the other person that actually have done. So the future, we now use multi-models to combine them both and see how they actually will interact. So then we can actually have an experiment. That's all my presentation. Before I finish, I just want to attract your interest for IITBR. Our next conference will be next year, and the deadline is September. So please send your abstract. Thank you. So how can I stop my screen sharing?
Great, Yusak, thank you. So there's a couple of questions in the chat to start with, in the Q&A. So do you also use Vienna test system, for example, differential stress inventory?
At the moment, we haven't really done so. But well, we use these NASA scales that we actually have, and then we try to find correlations with the EEG. And then we do actually have a high correlations between those. And then we also, the sensors also actually have different sensors of the brains. They're actually 3 different, this lambda, theta, and so on. They're actually also very consistent. But then we haven't done this Vienna test system. DSI.
Thank you. Prateek, he's got a question.
Yeah, thanks, Yusak. This is very exciting setup, I think. So I'm curious, like, are you thinking about studies on level of service which rely on interaction between pedestrians and cyclists? So I think the literature that I've seen so far, they have hard time in, varying the road width in the real experiments, and you can do that very easily in this environment. And there might be other factors which can be incorporated in the level of service measures for cyclists and pedestrians through this. So that's what I think the value of this from the level of service perspective. So I was just curious, are you thinking in that direction to do some progress?
Yes, definitely. So currently, the way we, for example, deploy the pedestrians and so on, we actually do in a rather controlled way, but then have a different set and context would be actually interesting. And at least on our sides, what we also do is from next year, we're hoping to also have a pedestrian simulator integrated to our system. So we can also include a real behavior that also will be shown in a VR. environments from the other mode's perspective, but then it's actually another real persons on the other side, which I thought then it's actually enable us to actually, as you said, testing many different things.
Very, very exciting. Yeah. Thank you.
So I've got one quick question. So actually, it's very in line with Prateek's comment in terms of, I agree, I think you've got a very exciting setup here. And in particular, I was wondering whether the fact that you've got this virtual reality version of Vienna, how much you can do with that in terms of the fact that some people will know the streets they're on. So just as an example, in that example you gave, perhaps the level of stress might also relate to how well they know where they are. So if they're in a street they know, for example, that might make it much more comforting.
It's actually a very good point. Yes. At least this is our so far concern is because people knew the area where they live, they would complain to us that this is not immersed enough. But then, and this is as feedback that we keep getting. But then you're right, because probably people familiar, then probably they're much more relaxed. We should actually, yes. I'll note that down. So then next time we will do it.
Okay, yeah.
In autumn, then we will actually ask that.
Cool. Yeah, no, I think you've got a nice setup. So there's, yeah, you see what you can do with it. I think it's, yeah, sounds great. Okay, thank you, Yusak. We'll move on to Bastián now.
Okay, thank you, Thomas. I'm going to turn my screen.
Right.
Can you see my screen?
Yeah, it's just loading.
So can you hear me well?
So yeah, I can hear you.
Okay.
Can hear you perfectly. It's just still saying I started screen sharing, but not actually. No, that's just me.
I can't also see the screen. It's still processing.
Yeah.
Maybe you
I'm
can
gonna do it again. Yes.
Yeah.
Now? No.
Not yet. It's odd. It seems like you do have permissions because it says starting screen sharing, and then.
Yes, but my internet is slow today, so maybe.
Okay. I'm going to turn off my video, just in case it makes a difference. Turn off videos. Ah, yeah, there we go.
Oh, yes.
Yeah,
okay.
I can see your slides now. Thank you.
Okay, sorry for that.
No problem.
Okay, so hello everyone. I'm going to present now this a part of my PhD dissertation. I work with my co-advisor, Professor Angelo Guevara, and Professor Ángel Jiménez Molina. This work is entitled Modeling Experience-Based Choices and Identifying Instant Utility, Latent Emotions using Psychophysiological Indicators. So this work is under review in TRB, so you can scan this QR code to see the preprint. I'm going to start by talking about this work of Kahneman et al. From 1997, who introduced these concepts of instant utility, experience utility, remember, and decision utility, revisiting Jeremy Bentham's work. Under his view, instant utility is a measure of an hedonic measure of satisfaction at a moment. So in a given experience, you will have a set of instant utilities that reflect the instant level of satisfaction with the current experience. And after that, all that set of instant utilities will be aggregated into a memory that will then influence the utility in the next episode or choice task. I'm going to try to turn on the camera. And this is interesting, but this framework ignores the role of attributes information. So they assume that people just decide from the experience, and it has very important measurement issues. Since, for example, Kahneman didn't handle instant utility as a latent variable, but as a variable that could be directly measured from stated responses. And Kahneman himself pointed out that the methods they were using should be supplemented by physiological indices of stress and hedonic states that we know nowadays that are correlated with psychological stimuli or psychological states. Yes, and this framework has been previously discussed in trial behavior literature. For example, in Tommy Carlin and Just DeVos, and also in the book of choice modeling by Daniel McFadden. But still, it lacks a clear discrete choice modeling framework. So our first research question is, how can we merge this well-established framework of integrated choice and latent variable model and Kahneman's framework? And the second question is, how can we measure these instant utilities by using psychophysiological indicators? I'm going to start with the first part where we propose the experience-based choice model that integrates both frameworks, the canonical choice and latent variables and the experience framework from Kahneman. So here we are seeing the part of the choice and latent variable model, but with the slight difference that I'm calling the utility, the decision utility, to be current with the other framework. This decision utility is a function of latent variables and exogenous information. Can you see my mouse? I'm pointing.
Yes, we can.
Things.
Thank you.
Yes. Okay. Thank you. And exogenous information about the attributes of alternatives, and with that decision utility, you make a choice. Basically, that is the same that always. But here the difference is that we care about what happens after you make the choice. So let's suppose you choose to travel by bus. When you travel by bus, you are exposed to a lot of stimuli. For example, the noise, the brightness, the CO2 concentration, crowding. I don't know, a lot of stimuli that generates a level of satisfaction in each moment, and that is represented by instant utility, or hypothesis is that can be measured by stated emotions and the psychophysiological indicators. And at the end of the travel or the experience, the instant utilities can be aggregated into a remembered utility through a memory aggregation process that is like a function that must be defined. And in the next episode, this remembered utility will affect or will influence the decision utility about taking the bus or not. And here we suppose that the remember utility can be measured by post experience stated emotion. And one important implication is that if we go a little bit here, if you take the curve of instant utilities, you can have a measure of the utility of with the complete experience, and that is called the experience or total utility. I'm not going to the details of this formulation. Here in this presentation, I'm going to focus on a case study where we applied this part of the model just to see if we could identify instant utilities. And we are currently working on a Monte Carlo simulation of the complete model. And this case study is reported in Barria et al. 44 participants took part of this experiment, all of them students from the faculty. They were asked to make a trip in the public transport network from Santiago. They use in different stages two kinds of buses, a low standard bus and a high standard bus, which is electric and has air conditioning and it's very comfortable. And one is totally the opposite. In some parts they travel by metro, and in other they walk. Each participant was using a biomonitor that measured physiological indicators such as heart rate, skin temperature, electrodermal activity, heart rate, and heart rate variation. And they also have this contextino, which is a set of environmental, which is a set of sensors that measure environmental variables as the noise or humidity and temperature, and other variables. And they also were asked to periodically state a psychological state or their emotion at that moment. For doing that, the circumplex model of affect was used, which categorized emotions according to two dimensions: the balance of the emotion and the activation of it. So an emotion with a positive balance is a pleasant emotion, and with negative balance is an unpleasant emotion, and the activation denotes like the level of excitation of it. So there are four quadrants that come from the combination of both dimensions, and the participant could state one of those quadrants. And also, each participant was accompanied by an observer that reported the travel variables in a mobile application. So the travel mode, or if the participant was seated or was sat or not, etc. And to model this, we model the instant utility explained by environmental variables: CO2 concentration, brightness, noise variation, temperature, and humidity, and by travel attributes: the travel mode, crowding, being sat or not, the travel time, the velocity of the transport mode, and being waiting or not. And this instant utility, in the other hand, explains the stated emotion and the psychophysiological indicators. We just use the sex of the participant as explanatory variable because was like the only demographic variable with variance in the sample. To simplify this classification of emotions, we did two models. In one model, we just use the balance of the emotion as here, and in the other model, we just use the activation of the emotion, binary. So the result. This table is very hard to read because it's very huge. But are the parameters, the estimate for the parameters of both models. This model MV explains just the balance of the motion, and this just the activation. To simplify this representation of the results, we took just the significant parameters of both models and took the quotient between them and the absolute value of the travel time parameter to just see how the effect size relative to the travel time, which has the biggest absolute value. So there is a hand up from Prateek.
I'm sorry, you can continue. Yeah.
Okay.
I'll just lower the hand. Yeah.
Here we are showing the graph that we built following the logic of the circumplex model. So here the x-axis represents the balance, and the y-axis represents the activation, and each dot is the quotient between the significant parameters and the travel time parameter. So you can see here that the travel time parameter is has minus one value for both axes, for balance and for activation, because it was like the worst attribute, that the attribute that caused the lowest instant utilities. Then after travel time comes the crowding level. These three dots here represent the three different levels of crowding that were considered. If the variables are in these quadrants, represent that these variables cause sad emotions. If they are here, it means that they cause happier emotions. So crowding is here because it's a bad variable, and using the high standard bus cause the happiest emotions. When the bus, the velocity of the bus is fast, is above the mean velocity. And if you see here, using the high standard bus, when the velocity was slow, is worse than when the velocity is fast. But interestingly, if you go to the other side, here is the low standard bus. When the velocity is fast, it is worse than when the velocity was slow. And we think that is because of insecurity sensations about aboard of those buses. And regarding the environmental variables, the humidity and the humidity, temperature, and noise were significant. I want also to say that we estimated the model omitting this part, just using the stated emotion as an indicator. And doing that, no environmental variables resulted to be significant. We just could see those effects by incorporating the psychophysiological indicators. And we also considered intersubject variation in the measurement equation of physiological indicators. Here we are showing the posterior distribution. The filled area plots are the posterior distribution of these parameters. We did this because we wanted to see if it was possible to obtain the measure of instant utility just by measuring the psychophysiological indicator. So, for example, if you measure skin temperature by seeing this equation, you can think that it's possible to obtain a measure of instant utility just by taking the quotient between the skin temperature and this parameter. But if you see the posterior distribution, it turns out that there is a high variation, and despite the mean parameter, the mean of the parameter is negative, there are participants for whom this relation is positive and others for whom it's negative. So it's not very directly, you cannot directly get this measure of instant utility just by measuring the physiological indicators. And these plots here are from the model where just balance was considered, and from the other model is like the same conclusion. And finally, the last result I want to show is that we can use this information to detect which part of the city causes the worst or the best emotions. So here we are seeing the probability of stating an emotion with a high balance. The more blue the dots are, means that the probability of stating a emotion with high balance is higher, and the red dots mean that a low probability of stating a high balance emotion. And here in this part, in this part of the route, the participants were using the lowest standard bus in shared lines, and resulted that this part of the route was the worst. And in the bottom, the participants were traveling by the high standard bus from B to E. Sorry, they were traveling by high standard bus, but just from D to E, they were traveling by high standard bus in segregated lanes. In all the rest of this part, they were using shared lanes, and you can see that in segregated lanes, the emotions were better. And the metro in this part, they were traveling by metro, was not significantly different from walking. So some conclusions: the EBCM joins the interactive choice and latent variable model with Kahneman's framework. And using data from a real-life travel experiment was possible to identify the effect of environmental and travel variables on instant utility measured with psychophysiological indicators. And the inclusion of these indicators increases the efficiency of parameters estimation and allows the identification of the effect of environmental and travel variables. And the use of portable devices to measure psychophysiological indicators could support transportation policies because of this, the last result of that I showed. And finally, the population parameters should not be used to infer instant utility from physiological indicators without calibration by individual. So thank you very much.
Great, thank you very much. We've got a question from Prateek.
Thanks, Bastián. I think this is a commendable effort to incorporate the instance-based learning with the sensor data. So I wanted to know, like, I have done some work on instance-based learning recently on route choice, actually, and that was in a statistics journal. So you might have missed that part, but I'll share that with you. But my question is, when you do the instance-based learning, then there is a memory parameter into it. And calibrating that memory parameter is very difficult. So when I was estimating my own model, I was not able to pin down that memory parameter by likelihood maximization. So I had to do the line search, like fixing the memory parameter, grid search basically, to find that memory parameter. So I wanted to know your experience. Are you also using that alpha type of a memory parameter, which is in the power form, which is very difficult to calibrate, or you are using different formulation of instance-based learning?
So thank you, Prateek. Yes, I know the parameters very hard to estimate, but now I'm not actually working with instance-based learning. Maybe I didn't explain it very well, but here the instant utility is just a latent variable that explains the choice of the emotion that the people state. So we didn't model a learning process in the trip of the participants. We just modeled the moment by moment choice of emotion.
Then I would be very reserved to call it an instance-based learning, because we are not using the learning part, because the main aspect of instance-based learning is to use the past experiences, store that in the memory, and then use it now. Yeah, I'm just curious if there is a way that you can account for the fact that they had some different experience in the past and now.
Actually, yes. I'm working now in the model of in modeling the complete framework, and to model this, I will use instance-based learning and reinforcement learning. I'm going to compare both learning models. Yeah, as Angelo said in the, I think, chat, you're also finding it hard to estimate the memory parameter. Okay, understand. Yeah. Yes.
Yeah. Thanks.
Thank you.
I've just put the paper in the chat box. In this paper, we actually incorporate the instance-based learning in the dynamic latent class model. And it's also a route choice.
Great, I'm going to read it.
Great.
Okay, that's we're just a couple minutes past the time, but yeah, you've got your email there. So any further questions can be directed there. I've got a couple, but I'll email you those later. I've got something else and other things I need to email you about anyway. Yes, it's been great. Thank you again to all of our speakers. And I hope you've had a great BTR conference. I believe it's pretty much finished now. I think that was the end of it. So yeah, thank you all, and hopefully see you all in person at IATR or something similar. So great, thank you very much, and goodbye.
Thank you, Thomas. Thank you, everyone.
Thank you, Thomas.